È molto importante iscriversi per la cena sociale, perché dobbiamo comunicare entro mezzogiorno chiaramente le adesioni. It's very important that you register for social dinner, because before, in the morning, you have to declare this. Il magnifico rettore viene direttamente lui, no? Mi hanno detto di sì, però Marina, i cavallerini non ci sono, i nomi ci sono? Sì, anche sì. No, lui dove anch'io, sì. Oggi se ne scappa. Sì. Vedi se c'è scritto là. Stiamo aspettando ci sono già molte delle autorità che hanno il piacere di fare un welcome speciale per questo 38esimo Congresso Nazionale degli Storici della Fisica e dell'Astronomia, e aspettiamo il Rettore dell'Università di Messina, che ci ha confermato la sua presenza, quindi sembra giusto. Speriamo che il tempo sia clemente. Purtroppo oggi è annunciata anche una meteo alert starting from 13 p.m. and le due lingue, italiano e inglese, qua saranno mescolate, va bene, come voi preferite. Essendo questo un congresso nazionale, a nome del consiglio direttivo credo di poter parlare, diciamo, l'italiano è per noi di estrema importanza, ma ovviamente la lingua scientifica è l'inglese, e quindi tutti gli speaker possono scegliere di parlare sia nell'uno che nell'altro, evitando di mescolare le due lingue, come ho sentito fare in qualche occasione, ma non qua ovviamente tra noi. I take a few minutes just to start waiting for the rector. I would like to thank all the speakers and the participants for the important, I believe, basic contribution to the scientific program. Thank you very much for that. This is the 38th Congress of Società Italiana degli Storici della Fisica e dell'Astronomia, and I would like to remark that it's the second time in the last 5 years that we have this Congress in Sicily. So the previous one was in Catania, Cireale, and Syracuse, if you remember. So I would like to thank very much the board of CISPA, and in particular the president, Lucio Fregonese, for the important recognition of this contribution. We would like to thank all the institutions contributing to support this Congress. Thank you very much. This INFN, sezione di Catania, with Department of Physics and the Laboratorio Nazionale del Sud, and Centro Siciliano di Fisica Nucleare e Struttura della Materia, and Dulcis in Fundo from Catania, the project Lauree Scientifiche Fisica, represented the national level by José Timmé. We'd like to thank for his important contribution. And evidently the local organization, Department of Mathematics and Physics here, and academia is really for us an important success. Thank you very much for that. This year the Congress is devoted, in addition to classical themes of CISPA, the history of physics and astronomy, to the figure of the astronomer Angelo Secchi, to the physicist Ettore Majorana. And we want also to commemorate, remind us, the 50th anniversary of the racial law against Jewish in 1938, that is an important occasion to think about history also. And by reminding some of the figures of physicists and astronomers who suffered the most from the disaster. So with this very poor and few words, I think we can start our Congress, and waiting from the rector, I ask Lucio Fregonese to give us a welcome.
Thank you, Angelo. I give all participants a warm welcome, and I thank Angelo for being the engine of this conference, which is involved with different important themes and anniversaries, as Angelo already reminded us. And attention was put to treat these themes with up-to-date scholarly research, and so an effort was put to invite scholars doing research in those specific fields, the effects of the racial laws on science in general. Angelo Secchi, one of the fathers, considered one of the fathers of modern astrophysics, and Ettore Majorana, and the 80th anniversary of his disappearance, and connect the themes because also the context is very important. Fermi, and we will have talks considering not only Majorana but also Fermi, Pontecorvo, and others. The opening session this morning is a sort of summary of the themes which we will address during the conference. And it was a good idea of Angelo to introduce all the themes with one talk in each of the various areas. So this will be just to taste the conference. The conference has been possible thanks to many institutions and individuals involved in the work, and so I would like to thank the local institutions, the University of Messina, and the Accademia Peloritana dei Pericolati, which is hosting us and which is part of the university, the INFN section of Catania with the director in Solia, Laboratori Nazionali del Sud, director Giacomo Cuttone. I would like to thank also the Progetto Lauree Scientifiche and the cooperation of Josette in me. This connection is important with students and with the school and with the university. The conference will host an important event, which is the first best paper, the first CISFA Best Paper Prize for young scholars. This is the first time we give a prize, and this is a sign of attention to young scholars. And another one will be an invited talks by recent initiatives in the world of students from the bottom. There is a need of history of physics, history of the disciplines. The students normally study in their university courses, and so we will have other younger people giving their point of view on the disciplines, on the importance of our disciplines, the history of physics and astronomy. I would like to thank also Enrico Giannetto, who in particular made possible the talk, the cooperation with Professor Eilif, and we will start with the fascinating topic, always fascinating topic of Newton. Okay, so.
I would like to invite Antonio Insolia. For INFN, director of INFN.
Thank you so much, Angelo. Good morning, ladies and gentlemen, dear colleagues. It's a pleasure for me as director of the Catania division of the National Institute of Nuclear Physics to welcome you to Messina and to Sicily. Well, actually the weather will be in the next few days not so nice, but I hope you will enjoy anyway your stay here in Sicily. I don't want to waste your time. Just I want to say that I don't need to remind you how important is history of science and history of physics to understand our roots, where we come from and where we are going. When I was student at physics, so many years ago now, I had a course in history of science, mainly focused on history of physics. Was Renato Pucci, my teacher, and he's planned to give a talk on Guglielmo Marconi, I think, on this in this conference. Actually, even if he was not how to say an historian of was not working specifically on history of science. He is a solid state physics. Actually, he's now emeritus professor in Catania University. I remember very much the way he was specifically focusing on Galileo and Newton, and this has been really a sort of guide forever in my life. Okay, so thank you so much. Enjoy this day and the conference. Thank you so much for being here.
Good morning to all. It's really a pleasure for me to be here on behalf of the Department of Mathematics, Physics and Earth Sciences. And it's the first time probably for me in an occasion like this, and I'm very, very honored, and I wish to thank the board of the organizer and the society, the board of the society. Just a comment. I think that the history of science, and particularly the history of physics, I'm a physicist, of course, like some of you know me, it's something in which we are interested in the later part of our life, or our academic life, or probably depends, because in the early years we are very focused on going forward, and for this reason I think that occasion like this, they are very important for young people to meet the importance of the historical part of every science, in particular of physics and astronomy. So thank you again to the organizer and to the society for this good occasion. Have a good work and enjoy your staying in Messina. Thanks.
Professor Paolo Giaquinta for the Academia. It's a very, very beautiful place where we are. Please.
Dear colleagues and students, distinguished guests, ladies and gentlemen, good morning. It is my great pleasure to welcome you all on behalf of the Science Division of the Accademia Peloritana dei Pericolanti, which I have the honor and privilege to represent. This academia, which has extended its patronage to the present scientific event, is an ancient scientific society whose founding dates back to 1729. It was called Peloritana after the name of one of the chips, Cape Peloro of the island, Sicily, in which the city of Messina is situated, and dei Pericolanti, because as a ship at the mercy of the waves, passing with the sails unfurled between Scylla and Charybdis, so in learning the scholar is tossed between difficulties and adversities in his search for the principles and laws that rule nature and the universe we are a part of. Indeed, as you can see, the coat of arms for the Academy bears the motto Inter utranque viam, a Virgilian reminiscence, periclitantes, always in danger. But understanding nature also requires putting experimental facts and theoretical constructs into a proper historical perspective, through which we can gain insight and intellectual discernment, which is what you precisely do with your precious work and research. So let me finally thank you all for your presence here. I heartily wish you an interesting and a stimulating meeting, and I hope a pleasant stay in this city of the Straits. Thank you. Arrivederci.
Giuseppina Aimè, President of Progetto Lauree Scientifiche. It's a very important project in Italy concerning physics and astronomy. Please, Giuseppe.
Okay, thank you. It is a very pleasure for me to be here in this very beautiful location, and to say to you the welcome from the Lauree Scientifiche community. But first of all, I want to say my compliments to organizer committee and or scientific committee for the very rich and very interesting program for this conference. The Lauree Scientifiche project is a national project with the aim to involve the students of the high school in the laboratory activity, but not laboratory as a location, only a location, but in the sense of a method through which is possible to involve and to elaborate also thinking, and so I think that the point of the historical point of view is one of the mezzo is an instrument to involve more and more the students. So I thank you very much.
So waiting for the rector, and we'll continue our conference because it's time to start with our chairman, Lucio Fregonese, and I'd like to thanks once again Robert Eilaf, because it was just impossible to stay here and in fact he found just a windows of 5 hours to be here. Thank you very much, Robert.
Okay, so I invite Professor Robert Iliff. He's Professor of History of Science at Oxford University. He has written in 2016 a beautiful book on Newton and Religion, Priest of Nature, the Religious Life of Isaac Newton. He has been for 15 years the director of the Newton's Theological Papers project, and he is currently one of the general editors of the Newton project, as well as co-editor of the Annals of Science, the prestigious journal. And he will give us a talk regarding the evolution of Newton's scientific method. And so thanks and welcome.
Thank you very much for inviting me. Grazie, Angelo, in particular. Yes, I have been very difficult. I have been very difficult, and I apologize. I'm going to talk about the evolution of Newton's scientific method. I will show you some images of the manuscripts. I will talk about his early work, and then go on to I'll finish by talking about the dispute with Gottfried Leibniz, and talk about the Principia Mathematica as well. So this is the person. This is taken while he was not taken, but a photograph. He was painted by Godfrey Kneller in 1689, when he was a member of Parliament after the Glorious Revolution. So this is the earliest picture we have of Isaac Newton in 1689. Still a relatively young man, but his best days were over. He had published the Principia 2 years earlier. Is this better? Can you hear me? Okay, great. Right. Newton was started reading his natural philosophical, his scientific textbooks at a time when there was a great revolution in science. He was lucky in that regard. Albert Einstein said he was a lucky man, as Einstein himself said about himself. Newton went to university at Cambridge. He studied Aristotelian texts, and then at some point, very, very quickly, in early 1664, he gave up reading Aristotelian texts, and he read the works of Robert Boyle, Galileo, Thomas Hobbes, the Cambridge Platonist Henry Moore, and most importantly, the works of René Descartes. Descartes was an inspiration for Newton early on. He was also a foil. He was a target against which Newton would work later on. The kind of approach that Descartes adopted was one that we call very generally the mechanical philosophy. The mechanical philosophy is both a cosmology and a methodology. So that is, the assumption very clearly is that the unseen world is made up of a plenum. It is full, it's plan, it is full of microparticles, and every natural phenomenon is explained through the motions of those particles. So it functions as an explanation and as an ontology. It is what there is in the world. Descartes, in a number of works, put forward an extremely intelligible, comprehensible theory, and his work was extremely popular across Europe. But as we will see, and I think it's not generally known, many of the English natural philosophers, some Dutch natural philosophers, thought that and in fact even Descartes himself to some extent emphasized the fact that his philosophies were the fictions of his own brain. They were fabrications or novels. They were stories or narratives. They were romances at a time when novels were just starting to be written. And it is that element of fiction that Newton, being a good Protestant Puritan, that kind of fiction is something he hated very much in himself as in the natural world. So for Descartes, there are vortices or tourbillons that swirl around large heavenly bodies like the Earth. These are swirling fluids of matter that force particles downwards to cause gravitation. On the left, there is a star in a vortex in a solar system. So stars are suns, suns are stars. In Descartes, there's a beautiful picture on the left. On the right, there are a group of solar systems, or what the science fiction TV series called star systems, which is a better phrase, I think. And there is a comet passing through various star systems. And this system has the benefit of being picturable, imaginable, and also comprehensible. It is intelligible. It looks as though it's plausible. It is not the kind of sympathies and antipathies of the medieval scholastic writers. And that is why Descartes' work and that of other mechanical philosophers was extremely seductive. It seemed to be a quintessentially modern, plausible way of doing natural philosophy. And as we know from the work of 20th century philosophers, the problem for Descartes and others was that his work explained everything. And we know that we should be suspicious of things that explain everything. Let me see. Newton started writing an undergraduate notebook in the end of 1664, so not long after he had encountered some of the modern writers. And early on, he was interested in a number of different topics. Let me see if I can bring these up again. I'm going forwards. Going backwards. Okay. Right. There we go. Newton was, I think, fascinating because the very first entries we have in his notebook show him already committed to an infinitely large universe. We know Descartes and many other natural philosophers were concerned about saying that the universe was infinitely large because if it was infinitely large, it might be God's body. So there are many problems with that. You also cannot imagine something that is infinitely large. Descartes has a series of ways of proceeding towards something that is infinite by denying successively what is finite, but it's not a particularly successful argument in his book, Principia Philosophiae. Newton was interested in a number of different topics right from the word go. In the very first 2 months of his notebook, he thinks that space is infinitely large. He also thinks, remarkably, that space is almost entirely empty. So it is vacuous. There's nothing in it, which is a remarkable thing to believe. He never changed his mind about that. He was committed early on to the existence of an ether, so something that explained electricity and magnetism, and that could explain gravitation. I mean, all through his life, despite what he writes in the Principia, he believed in the existence of an ether, but of course you cannot, as far as he is concerned, you cannot see an ether directly. He's interested in comets. Here are some notes, very early notes, about the sun, stars, and planets, and you can see on the top right he's added "and comets" afterwards. The very first notes here are from Descartes, the Principia, thinking about how Descartes might explain a comet. And this is Newton, a typical quintessential Newton way of proceeding, which is to take notes from a canonical source and to question that source in, as we will soon see, in a way that provokes a kind of experimental test of that source. He does not lack ambition, and he is incredibly ambitious, which of course is a necessary condition of being successful. You may also see, if you can read his writing, he goes from talking about comets to the Bible. So for Newton, it is a segue. It is a seamless transition from talking about a comet to Hebrews chapter 1, verse 2. God made the world by his Son. And then there are notes on a comet of 1618. All these things in Newton's mind are connected. Here at the bottom of the page are Newton's famous first notes. This is the same page. Are his famous first observations of the comet of 1664. And we don't have time to go into detail, but that's his drawing of the comet as he saw it, of late 1664. And he added the word "of comets" at the top of that page once he saw once he realized that the comet of 1664 existed, and he then went back and took notes on the comet of 1618. What else? He's interested in gravitation. Again, this is something that shows right from the start he's fascinated by the issue of gravitation. He is fascinated by, and again, a remarkably powerful critique already of any Aristotelian explanation of motion in a plenum. The very first thing Newton says is that motion in a plenum would be motion in a resisting medium. So this is the origins of Book 2 of the Principia, already in the very first writings that he put forward. You know, unlike the Aristotelian or Cartesian systems, Newton says right from the start that motion in a plenum would stop the object from moving almost immediately. So there cannot be a plenum. So most of space is empty. Okay. In the middle of the 1660s, as we know, Newton discovered the heterogeneity of white light. White light is heterogeneously composed of more basic primary rays, each of which has its own index of refraction, and each of which secondarily gives rise to a color, but a color is not an essential quality of a primary ray. Newton discovered the algorithms of the calculus in 1665 to 66. He showed pretty nearly, as he said, that the law that governs the force pulling the moon towards the Earth is the same as the Galilean law of free fall. He showed that pretty nearly, as he said, but he stopped that program in about 1667. So it stopped in its tracks, and it is not universal gravitation. This is nothing like universal gravitation, but it is, of course, a momentous effort to show that the celestial and terrestrial spheres can be linked through mathematical law. And Newton was made Lucasian professor in 16 1969. As a very young man, he was only 26. And his first lectures were on geometrical optics as a paean, as a hymn of praise to his tutor. He was Isaac Barrow, the first Lucasian professor of mathematics. And I think what historians have found interesting is in those lectures in 1670, Newton argued that geometers should try and learn more natural philosophy, and natural philosophers or scientists should learn more mathematics. And already there he says, science, insofar as it is properly science, is absolutely certain, and the only way to get absolute certainty is through mathematics. It's through resting science on mathematical foundations. He makes a very concerted attack on probabilism, that is, the idea that all we can know about the natural world is probabilistic. What Newton says is, we can know certain things, we can know facts about the world, we can know some theories with absolute certainty. And he writes this, he delivers that in his lectures of 1670 to 71. And this, of course, transfers into his published work on light and colors in 1672, the first, and again, for Newton scholars anyway, the famous enunciation of the heterogeneity of white light, that Snell's sine law of refraction applies to each individually partitioned primary ray, which is a remarkable discovery, and it's one that's not accepted by the majority of his critics. He does it by means of a crucial experiment and very, very careful measurements. Newton suppressed, and I think this is important, crucial for, I think, science that comes after Newton. Newton, at this point, unlike in his earlier work, where he'd been a committed corpuscularian, in his published work, Newton was already trying to suppress any commitment to the physical reality of a light ray. So already in that paper, and particularly in responses to the paper, Newton moves away. He withdraws from saying whether light is a wave or a particle. He is going to talk, as he says, abstractedly or neutrally or generally about what a light ray is. And this is perhaps the quintessential Newtonian move. This is what happens when you bring mixed mathematics into the domain of natural philosophy, as it were, the kind of Cartesian or even Aristotelian stuffiness, the physicality, the concrete, tangible stuff of the world is hollowed out. Newton gets rid of it. It is not part of science, or it is to be, or it is something you do in private, or it is something to be deferred into the future. For now, to achieve certainty, the price of achieving certainty is to talk abstractedly about a ray of light. And again, remarkably, nobody had done anything like this. Newton's definition of what a light ray is not, of a primary light ray, is not its color. It is its index of refraction. It's not its color. It's its index of refraction. That is what it is. So this is an ontological claim, as it were. A light ray is its index of refraction. It is, and you need to measure it very carefully. Newton was stung by some people. Christian Huygens and Robert Hooke made a number of criticisms. Robert Hooke sensed correctly that Newton was really a corpuscularian in terms of light, and he said that corpuscularianism, like your theory of white light, is merely an hypothesis. And we know that Newton famously hated being accused of merely putting forward hypotheses. What Newton traded in were absolutely certain propositions. And throughout 1672, in response to his critics, Newton became more strident, more hysterical, more shrill, and it's in a couple of letters in the middle of 1672 that we see Newton's first detailed statement in methodology, which is to say, repeating what he had already said to some extent, or extending his work in his Lucasian lectures. For a piece of natural philosophy to be properly scientific, it has to be mathematical. It has to be mathematically certain. Otherwise, and this is the great Newtonian move, I think, or one of them, your hypotheses are just opinions. They're like online comments. They're worth nothing, right? They're simply pieces of fiction that come from your mind. Unless you have corroborated what you've done with many experiments, with astronomical data, and so on and so forth, what you put forward as a hypothesis, particularly when it's publicly stated, is merely an imagination. It's a fiction. It's a Cartesian romance. And Newton's account of hypotheses is very, very negative. It's very extensive. In Newton's world, in his ideal world, almost only himself, Galileo, Christian Huygens, and a few others count as proper natural philosophers. And his attack on probabilism is an attack on some of his colleagues in England who are probabilists, who are experimentalists. What he's saying to them is, unless you have the mathematics to underpin what you're doing, your work is worthless. And he practically says that to his colleagues. On the other hand, if you compose great mathematical theories without evidence, that is also a fantasy. Or it's just mathematics. And I think also the point at the bottom I make here is very significant. It is that Newton is saying something about the scientific community. Newton has an implied view about the scientific community. The scientific community cannot rest on a group of people who put forward mere hypotheses, mere opinions. It has to be based on consensually achieved sensory, observational, and experimental evidence. Newton did use hypotheses on a number of occasions, and he regretted doing so. He published hypotheses. One of these was in 1675 in a paper that's called The Hypothesis, which he sent to the Royal Society, and he became immediately mired or embedded in the kind of dispute that he had said hypotheses led to in the first place. So in a sense, the publication, the reading of his hypothesis at the Royal Society gave rise to the very kind of disputes, and I think crucially about intellectual property and honor that Newton despised. And Newton continually said, if you engage in disputes, if you promote hypotheses too much, science will descend into a cacophony, an anarchy of opinions. We can do better than that. You know, this is a world that is created by God. We have a duty to understand it properly, as it really is. And I think in the tradition of Christian Huygens, in the Horologium Oscillatorium, as many of you know, Newton put forward 9 hypotheses in the first edition of the Principia Mathematica, but they're not really hypotheses, and they're a very peculiar species of statement that were removed before the second edition. I want to just briefly go through what I think is a key issue, which is the comet of 1680 to 81. This was perhaps the that appeared in the last 1,000 years. It was very frightening to people. It's a major event in the heavens. And people wanted to know what it was. It appeared at the end of 1680, and then it disappeared for a few weeks, and another comet reappeared in January 1681. And the question was whether it was the same comet or whether it was what were called one of a pair of comets that had appeared throughout history. The standard view amongst Newton's contemporaries was that it was one comet that had traveled in front of the sun and had been brought towards the comet through a magnetic force, and then had been turned around and then repelled by the sun, pushed away by the sun, to give rise to the event that was seen in January 1681. But Newton resolutely adhered to the idea that there were two comets, not one comet. And he got into a dispute, a correspondence with the Astronomer Royal, John Flamsteed. Flamsteed was very much of the opinion that comets were magnets with atmospheres. Lots of people, of course, at the time argued, as Newton himself would do, that comets were the bearers of life, and that comets were God's way of seeding star systems with life when objects move through them, and that has continued to be a very popular view until the early 21st century. This is John Flamsteed, the Astronomer Royal. That is a picture of a comet. It's an incredibly bright comet, the comet of late 1680. That's from Frankfurt. Newton argued that given the observations, if it had been a single comet and if it had traveled in front of the sun, it would have come to a halt for some reason, because it had taken too long for it to reappear if it had appeared in front of the sun. From his own experiments done as a student, Newton also believed that hot magnets do not work, so the sun cannot be a magnet. Therefore, the entire magnetical philosophy is false. There's no mechanism, Newton says, for it to be one comet, because the data suggests that the comet went round the back of the sun and then reappeared, but then if it did, which is what the data suggest, then we don't know what the mechanism is for the object going round the back of the sun. So logically, the simplest solution is that there were two comets, and Newton held on to that view for another 2 or 3 years. This is Newton's own drawing of a comet appearing from the bottom right. It comes up to the sun. The last observation is at K. And then Newton said to Flamsteed, if it had gone round the back of the sun, which is what the data suggest, it would have gone off the top of the page. So there's no reason, there's no mechanical reason for the object to have come all the way round the sun. D is where it reappeared in January 1681. So Newton logically held on to the view that there were two comets, but of course, if the magnetical philosophy is false, and if large bodies in the heavens exert pressure or force over distances in the heavens, this is a species of force that had not yet been enunciated by anyone in human history. And you can see that although Newton does not have universal gravitation, he's opened the door towards universal gravitation in his theory. The origins of the theory of the Principia Mathematica are well known. A visit from the astronomer Edmund Halley in 1684 prompted Newton to develop in an extraordinary way over the next year his theory of force, of mass, universal gravitation, etc., going far beyond what anyone had done before. It all hangs together. You know, you can't have mass, the concept of mass, without universal gravitation. You can't have universal gravitation without the inverse square law. and an idea about the influence that two massive bodies have on each other. Newton, to produce his theory, got hold of a wide range of astronomical data from various people taking observations in the French West Indies, in Scandinavia, in England when the weather was good enough, and from other parts of Europe. And he collated this data, bringing together data that suited his purpose to bolster what became Book 3 of the Principia. And Book 3 of the Principia, of course, deals with comets, with tides, and the oblate spheroidal Earth. I mean, these are the great triumphs of the Book 3 of the Principia. The crucial element in the Principia, as George Smith has pointed out, is measurement. I mean, Newton's methodological pronouncements are quite hard to find, so we have to read into what he's doing and saying, what it is he thinks people should do to get scientific knowledge. But we know from the pronouncement in the Principia Mathematica that above all he thought that the method of the Principia was a template or an exemplar that functioned as a theory of measurement. You make very, very accurate measurements. Somebody armed with the correct theory collates these pieces of data, and by induction, whatever that is, one generalizes to produce a mathematical law, and then, of course, by a reverse process, uses that law to explain the phenomena that had given rise to the law in the first place. So this is the method of analysis and synthesis. But as George Smith points out, it's much more complicated than that, because this is a super theory. This is, for Newton and his followers, a much deeper, richer, fundamentally unfalsifiable theory. If there is a discrepancy in the observation between theory and data, what are you invited to do? You're invited to say that the observers are incompetent, or you are invited to say that these peculiar discrepancies tell you something about the natural world. Newton's theory and the observations predict that, again, shockingly to contemporaries, planets do not move in ellipses. They don't. They are subject to an infinite number of forces operating on them at every moment. They can't possibly move in perfect ellipses, and the heavens are not perfect. They don't trace out the same orbits from one orbit to another. But what Newton's theory can tell you, or what it allows you to do, is what Clairaut and Lagrange and Laplace would do in the 18th century, which is to take into account the extraordinary force, for example, of Jupiter, to compute the return of Halley's comet. So you can use what you know about Newton's theory. Obviously, there are some moments when Newton's law of universal gravitation is shaky in the 1740s and early 50s, and it's the return of Halley's comet in 1758, really, that for the French at least, if not for the British, for the French, it shows that Newton's theory is true and remarkable. And Newton, I think, becomes a genius in France at that moment. You know, before that, he's verging on being a genius, but with the return of Halley's comet, the fulfillment of the prophecy, Newton becomes an extraordinary genius. So in the how do we think about the universal gravitation? It's a theory, but it's a true theory. Newton attacks all kinds of theories, but his one is true, luckily for him. Universal gravitation exists as a thing. What it is unclear. It's not like the mechanical mechanisms of art. It's not like corpuscular stuff that you can feel, almost feel, if you're Aristotelian or Cartesian. It can be invoked as an explanation for everything that goes on in the universe. So in that sense, it has that methodological ambition that you need from a theory that's true. And also, as the title of his book shows, The Mathematical Principles of Natural Philosophy, it is the crowning glory of a disciplinary realignment between mathematics and natural philosophy. Mathematics, as he had said in his optical lectures, mathematics should lie at the very heart of science. And if you didn't believe it was possible, or if you thought that was wrong or a fantasy, Newton had shown in his book that that is exactly how the world, or how one should go about doing science. Just briefly go through some criticisms of the Principia. Obviously, the way Newton proceeds is disastrous for many of his contemporaries. This idea of universal gravitation or attraction is a dereliction of duty for scientists. The goal of science, of natural philosophy, is precisely to explain things through physical causes, and Newton has thrown this away, and he's come up with something that is mathematically neutral, this idea of force. And of course one could go further than that and ontologize force. One could say there is this thing in the world which is force. It really exists. You can't see it, you can see its effects, but it really exists in the same way that corpuscles or Aristotelian elements were supposed to exist 100 years earlier. Others, like the French natural philosopher Louis Bertrand Castel, saw Newton's work as essentially a monster. He actually called it a monster because it's neither mathematics nor is it physics. And there are good reasons for agreeing with Castel. But by the standards of the day, Newton's work is impossible to categorize. I think that the strident mathematicism of Newton that we saw in his early work is softened very slightly in the last 2 decades of his career. It is not that he becomes a kind of Baconian inductivist. He remains a mathematician. He remains someone who believes that science should be founded on mathematics. But he is pushed by his critics to lessen the claims he makes about universal gravitation. But he does not let up in his criticism of hypotheses, and there are numerous, hundreds of private notes where he attacks hypotheses and metaphysical systems as fictions, as imaginary dreams, and increasingly as novels. I mean, he writes this at the very moment that in England, novels are appearing like Robinson Crusoe and Moll Flanders, and even just before Gulliver's Travels. I mean, he sees the products of Leibniz in particular as imaginations. Here is one response that he published in 1712. I don't know if you can read it. So Leibniz commends experimental philosophy, but adds that when experiments are wanting, it is allowed to imagine hypotheses. And I should say, although I don't have time, that Newton's hatred of the imagination, as I said at the start, comes from a religious hatred of the imagination as the source of idolatry, as the source of human fictions. The human imagination tempts us to mistake the products of the imagination for what are really the products of God. In the preface to the Principia by Roger Coates, the great follower of Newton, and also in the Rules of Philosophizing that appear in the 2nd edition, Newton again goes on at length about the dangers of hypotheses. In this, this is the most famous, and I think in the 18th century, the most significant methodological statement from Newton. In experimental philosophy, propositions gathered from phenomena by induction should be considered either as true or very nearly true, notwithstanding any contrary hypothesis. That means we've seen that universal gravitation is true on Earth. We should assume it's true throughout the universe, unless someone comes up with a better theory. But we know that Newton did not believe that anyone would ever come up with a theory that was as robust or corroborated as his own. It's highly unlikely. It's almost impossible that with all the great successes, this would be overturned, but of course it was. So Newton's hatred of hypotheses became part of 18th century intonations and liturgies of methodology from his followers. Hypotheses non fingo. We do not feign hypotheses. However, in private, Newton did talk about hypotheses. In private, in the queries to the optics, for example, bizarrely, he put forward a range of different functions for the ether, including gravitation. In the 1717 to 18 optics, in one of the queries, he said that maybe an ether could explain gravitation throughout the universe. But of course, the Principia militates against that to a very large extent. But then here's something very different. And I think the final thing to say in terms of methodology and hypotheses is, Newton is the arch anti-imaginativist. He hates the imagination. When he was asked how he discovered everything and did his work, he said it was by thinking on things for years, for 2 decades, for 3 decades. It is by working hard. And yet, in the 1750s, 60s, and 70s, when scientific methodology is transformed, it is Newton's imaginative power, his power of imagination, that is held up as the most striking part of what it is that makes science creative. And that is one of the great ironies of the history of science. Thank you.
Thank you very much for this fascinating presentation, long-term presentation of Newton, the evolution of Newton's method. We are a bit short of time, so I think, but there is time for one question or comment. Is there anybody? Francesco Guerra.
I'm asking about the connection between Galileo method and the Newton method.
Galileo is a hero for Newton. There are a few statements in Galileo, and I do not think Newton is indebted to them. But of course, Galileo comes from a mixed mathematical tradition. He is somebody who, on a few occasions, denounced the romances. I think he uses the term, or at least that's the English translation. The kind of multiple theories that various people had put forward, whether they're Neoplatonic or Aristotelian. He denounced these as figments of the imagination. So I think that is what mixed mathematicians do. I think that's part of their métier, is that they denounce these kinds of systems. And of course, the interaction between Galileo and Descartes in the late 1630s is wonderful, because Descartes says that Galileo builds without foundations. But Galileo has kicked away those foundations because they're not foundational for anything. And we can see that clash between Galileo and Descartes is replicated 50 years on. But Newton is writing at a time when the mechanical philosophy is becoming less fashionable.
Rob, as I remember, an alternative explanation of gravitation was existing at that time by Fazio and Le Sage de Douillet later. But this is Paschen gravitation, and it seems to me that it was a moment when Newton's attract much attention on that, but at the end he rejected. Do you have a comment on that?
Newton pioneers ways of avoiding talking about causes of gravitation. I think he knows with certainty that you cannot have a mechanical explanation of universal gravitation, because there is no mechanical explanation that can allow an atom on one side of an infinitely large universe to influence in real time an atom on the other side of the universe. You can imagine, as Christian Huygens does, a more local form of contact explanation for gravitation. But universal gravitation is really strange. And I think it's just as strange as quantum mechanics. It's just as strange as quantum non-locality. And because it is a version of non-locality after all. But Newton says in private that the cause of gravitation is God. That's his view.
Effect. It's not connected with the infinity or not of the universe. Just by pushing body, this elementary particle could produce an inverse law square. This is what's demonstrated. So I think you have done this work also. For this reason I suggest this. Okay, thank you.
Okay, thank you very much. Prossimo speaker, Fabio Bevilacqua, Università di Pavia, è stato anche presidente della Società Europea di Storia della Scienza, tra le varie cose, che ci parlerà di Theoretical and Experimental Formulations of Energy Conservation and Their Historiography. 25 minuti, ti faccio segno per comodità quando mancano 5.
Thank you very much to Angelo Pagano and Lucio Fregonese, especially to them, but also to the others. And I'm very glad that after 38 years, the society is still prospering. First conference was in Pavia 38 years ago, and I'm very glad that we are still around. So I'll basically talk about Joule. It's the bicentenary of Joule's birth, and there are a number of points. There will be no time to do all this, but just to give you an idea, there are experimental analysis of Joule's work, then theoreticians, then there was a big theoretical debate at the end of the 19th century. And then at the beginning of the 20th, the philosophers like Cassirer and Meyerson wrote books on energy conservation. And some of these books were very influential on Kuhn, and Kuhn's famous paper on conservation of energy of 1959. And today educators struggle to teach energy conservation and follow one or the other approach. Will be impossible in 20 minutes to talk about all that. But these people we will deal with, and this is an image of our guy, and some drawings of his tools. Now, Joule was an amateur. He started working on his own. When I was, I think that Angelo allowed me to speak in Italian at certain stage. Is that true? Yes, okay. Allora, quando io ero giovane leggevo che Joule era figlio di un birraio. Poi ho scoperto che il padre era un multimiliardario che aveva una delle più grandi fabbriche di birra, e questi esperimenti erano fatti anche perché Jules aveva una salute un po' malferma, con l'aiuto degli operai della birreria. Jules si è dedicato tutta la vita a fare questi esperimenti, principalmente a spese proprie, ed è finito con una pensione sociale perché la birreria nel frattempo era andata a ramengo. E, diciamo, questi esperimenti tentavano di essere estremamente precisi e diciamo, si protraevano ciascuno per parecchi mesi. Qui in basso a sinistra sono cominciati a maggio e a destra in basso invece sono proseguiti fino a luglio. Era lo stesso esperimento. Una moltitudine di esperimenti che cercavano di legare il lavoro fatto con il calore prodotto. Quello era del 43, quello che abbiamo visto prima, questo è del 78, quindi 35 anni dopo Jules continuava a fare esperimenti per determinare questo equivalente meccanico del calore. E una cosa interessante che va rimarcata è che Jules ha dei risultati diciamo, molto diversi dai suoi esperimenti. Non c'era una convergenza precisa e soprattutto i primi avevano un range enorme di differenza, e lui prende le medie di queste serie di esperimenti, poi cambia metodo sperimentale, ottiene dei risultati diversi e fa le medie tra i diversi tipi di esperimenti che fa. E questa, diciamo, è una pratica che, come vedremo, poi sarà criticata. Comunque ha il ruolo importante di far vedere che c'era una qualche somiglianza una discreta somiglianza tra questi risultati. Nel 1887 Georg Helm, un sostenitore dell'energetica, fa un'analisi degli esperimenti